The next type of a series that we can find the sum of is called the telescoping series. So what is it? So here is an example. This is the definition. So a telescoping series is basically something whose elements we can express as, well, an minus, well, using some other sequence as an minus an plus m, where the sequence an is known to us, right? So this is some known um, sequence. Here is an example. So what is this? So here we can see that the given series is the sum of terms, each of which is the difference of elements of another sequence defined by this equation, right? Now, why is it called a telescoping? Because basically the idea is that if you um, write down the whole sum, then it's going to sort of fold like a telescope. Let me explain what I mean, right? So um, if n is 1, then this is 1 over 1 squared plus 9 minus 1 over, uh, all right, so 1 plus 3, so 4 squared plus 9, right? So this is my first term, a1, plus the next term, a2, is going to be 1 over 2 squared plus 9 minus 1 over 5 squared plus 9. Okay, so now that there is nothing interesting yet, so plus, let me just go on for a few more terms. 3 squared plus 9 minus 1 over 6 squared plus 9 plus 1 over, the next term is going to be 1 over 4 squared plus 9 minus 1 over 7 squared plus 9. And then let me write down one more. So 1 plus 1 over um, 5 squared plus 9 minus 1 over um, 8 squared plus 9, and so on. So now notice that if you um, compare a1 and a4, I think so, this is going to be a2, this is a3, and this is a4. So if you look at a1 and a4, you will notice that there is the same entry in both terms. In a1 it comes with a negative sign, in a4 it comes with a positive sign, so they're going to cancel out, right? But then if you look at a2 and a5, there's going to be the similar kind of situation. Yeah, so minus 1 over 5 square plus 9 plus 1 over 5 square plus 9. And you can guess that if I add more terms, then basically all the terms that appeared in front of the series with the minus sign are going to just disappear, that they will be cancelled out, and so on. So then, and if you write down like a very long sum, then almost everything is going to cancel out, because almost all elements here are going to have a counterpart with a, well, with the same but with a negative sign, and essentially we are going to end up with just, if we write down the finite sum of partial sum of the series, then basically it's going to contain three entries coming from uh, the first three terms, and minus, well, three entries coming from the last three terms, and the rest is going to just cancel out. And this is the idea that will lead to a formula for the sum of an infinite telescoping series, right? So here is another example. So cosine of pi cosine of pi over n minus cosine of pi over n plus 2. So same thing. So if you write it down, it's going to be something like um, cosine pi minus cosine pi over 3. This is the first term, plus cosine pi over 2 minus cosine of pi over 4. This is the second term. The third term is going to be cosine pi over 3 minus cosine of pi over 5. And now notice that cosine pi over 3 cancels out. And then if you go on, the next is going to be cosine pi over 4 is going to be cancelled with this cosine pi over 4, and so on. And here is maybe one specific example before going on with the general formula. So let me show you how we can apply this trick to show that this series is convergent, and to find the sum of the series. Well, strictly speaking, we should write the sum. I mean, if it is an infinite series, then we say the sum of an infinite series, not the limit. So always say the limit of the sequence of its partial sums. Okay, so the first thing that we need is um, to figure out whether this is a telescoping series. And here that there is one neat trick that is going to work. Basically, if your series is a rational function, then what you need to do, you need to apply partial fractions. Well, this is something that you probably should have known from your poly or JC times, so I'm not going to get into details. So I'll just try the answer. So 1 over n times n plus 1 is 1 over n minus 1 over n plus 1. All right? Yeah. Okay. So now it means that a few first terms of our series are a1 is 1 over 1 minus 1 over 2. A2 is 1 over 2 minus 1 over 3. A3 is 1 over 3 minus 1 over 4, and so on, right? And what is the partial sum of my series? So Sn. So Sn is A1 plus A2 plus A3, and so on. We should add them up all the way to An. And this is going to be A1 is 1 over 1 minus 1 over 2. This is A1. Plus A2 is 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. So this is A3 and so on. So let me, this is A1, this is A2, this is A3. In order to illustrate my point, let me write, let's say, an minus 1. So an minus 1 is going to be 1 over n minus 1 minus 1 over n, and plus the last term, an is going to be 1 over an minus 1 over n plus 1. Right? And what you see here, almost everything immediately cancels out. So minus 1 half plus 1 half, minus 1/3 plus 1/3, and so on. So the only two remaining terms are one, the first one, and the last one. So this is really 1 over 1 minus 1 over n plus 1. So this is 1 minus 1 over n plus 1. And by definition, the sum of the infinite series is the limit of the sequence of its partial sums. So this is, by definition, is the limit as n goes to infinity of 1 minus 1 over n plus 1. And as n goes to infinity, this part just approaches 0 clearly. So this is just 1 minus 0, which is 1. Okay, so what we did is we have shown that this series converges because the sequence of its partial sums has a finite limit, and we also found this limit. All right, so the first step is to apply partial fractions to show that this is a telescoping series. Okay, so now the next step is to find an equation for Sn in terms of n. Again, so using the fact that this is a telescoping series, we are going to just write down as n explicitly, and we see that almost everything is going to just cancel out. And here is the equation that I just derived. And the last step is to find the limit by just taking the expression for Sn and finding its limit as n goes to infinity. And here the limit is 1. So which means that the sum of the infinite series is 1. All right. Cool. So now let me explain how we can apply the same method to find the sum of any telescoping series. So if we manage to express our series as a telescoping series, and if we know the equation for an, then we can always do it, right? So from basically the idea here is that we can write down the partial sums, and then if we manage to find the limit of partial sums, then we have found the sum of the series. All right, so now if you write it down element by element, so you will see that almost everything is going to basically cancel out, and the nth partial sum of our telescoping series is going to be the sum of first m terms minus the sum of last m terms. So it's just like that. Well, those last m terms meaning those that come after n. Now, this is an explicit formula for Sn. So, and now if we manage to find the limit of this expression as n goes to infinity, then basically we solved the series. So notice that this part is really just a constant. So this part is independent of n, right? So this is independent of n. So when you take its limit, nothing happens. Basically, you just get the same sum, right? So and when you take the limit of this expression, basically you have, I mean, you have several copies of the sequence an here, and you take the limit of each of them, but of course all of them have the same limits because they are essentially the same sequence, only by only it is shifted by one, well, by several positions. Like, I don't know, let me give you some examples. So if, let's say, if an is, what did we have, is cosine of pi over n, right? Then basically this looks like um, cosine of pi over n plus 1 plus cosine of pi of n plus 2, and so on up to cosine of pi over n plus m. But then if you take the limit as n goes to infinity, of course all of them are going to approach the same number, which is just the limit of cosine of pi over n, because all these sequences are essentially cosine of pi over n, just shifted by a few positions. Okay, so that's the idea. So which is why we get this answer, right? So if um, the limit of our sequence an as n goes to infinity is some number l, then basically when we take the limit in the partial sum of our telescoping series, right? Um, then we get the first m terms. So that are just the sum of the first m terms is just a constant minus m times that limit, right? And if the limit exists, then our telescoping series, well, converges. So a good question is, what happens if the limit does not exist? So does it mean that our telescoping series diverges, or it doesn't diverge? So you can think a little bit about it. There will be some questions in the quiz, but I will give you a hint. Usually the answer is yes. Usually the telescoping series actually diverges in that case if the limit does not exist. But there are exceptions. Okay, so here is our example with cosine of pi over n. Right, so here m is equal to 2. Right, so applying this equation, yeah, at the same time we know that the limit of cosine of pi over n as n goes to infinity, basically this part goes to 0, so we get cosine of 0, which is 1. Right, so it means that since the underlying sequence converges, it means that the corresponding telescoping series also converges, and there is a sum, and the sum of the series is going to be, well, here m is 2, so we take the first two terms, which are cosine of pi plus cosine of pi over 2 minus 2 times this minus 1, and this is cosine of pi is negative 1, cosine of pi over 2 is 0, so this is negative 3. So this is how we can apply the formula, and basically here is the same, only in print. So here the telescoping series converges to negative 3. So the sum of our telescoping series is negative 3. All right, so that's all about telescoping series. So please take the quiz, and I will see you after you do the quiz.